rational functions can look almost identical, but one has a whole and the other has an asymptote. Here's how to tell the difference every single time. A whole is a removable discontinuity. It happens when the function is undefined because a factor cancels. And an asymptote happens when the function blows up to plus or negative infinity. The graph shoots towards infinity. Once again, a whole appears when a factor cancels from numerator and denominator. For instance, for the function f of x equals x minus 3 times x plus 1 over x minus 3 times x minus 2, we can clearly see that we have the common factor of x minus 3 and x minus 3 in numerator and denominator. So therefore, we can cancel the factor of x minus 3 and we'll be left with x plus 1 over x minus 2. But the function is still undefined at x equals 3 because that will make the denominator 0. Therefore, this creates a whole. So the graph is a normal curve, but with one missing point, like a donut hole in your function. So how do we test for holes? If the factor cancels, there is a hole at that point that will make the denominator 0, and you would get a removable discontinuity. A vertical asymptote appears when the denominator equals 0 and no cancellation occurs. So first, you'll need to find where the denominator of the fraction equals 0. You'll need to check for cancellation. Does any factor cancel with the numerator? If the answer is no, then you have a vertical asymptote. For example, for the function g of x equals x plus 1 over x minus 2, no factor can be cancelled, but the denominator will be equal to 0 when x equals 2. Therefore, there will be a vertical asymptote at x equals 2. And the graph shoots upward or downward toward infinity near the asymptote. Here's our first example. A function f of x equals x squared minus 9 over x minus 3. First, we need to factor. X squared minus 9 can be factored out as x minus 3 times x plus 3. And now we'll have a common factor of x minus 3 in numerator and denominator. Canceling it out, we're left with f of x equals x plus 3. That is the equation of a line. But the function is still undefined when x equals 3 because that will make the denominator 0. So in this case, we'll have the equation of x plus 3, but there will be a hole at the point 3, 6 because the function is undefined at that point. Given the function h of x equals x squared minus 9 over x plus 2. In order to figure out if there's an asymptote or a hole, you'll want to factor first. So factoring the numerator, once again, x squared minus 9 can be factored as x minus 3 times x plus 3. In this case, nothing cancels with x plus 2 in the denominator. So we know there won't be any holes. But the denominator will be equal 0 when x equals negative 2. Therefore, there will be a vertical asymptote at x equals negative 2. Looking at the graph, we can see that the function shoots towards infinity as it approaches negative 2 from the left, and it shoots towards negative infinity as it approaches negative 2 from the right. Now let's compare side by side. Does a factor cancel? If yes, there's a hole. If no, you'll have an asymptote. A hole is a removable discontinuity, whereas an asymptote is infinite discontinuity. The shape of the graph will be a curve with a missing point for a hole, but for an asymptote, the curve will be exploding near that line. And then once again, how do we detect it? If there's a canceled factor, you'll have a hole at the point that makes the denominator 0. Otherwise, you'll have an asymptote at the point that makes the denominator 0. Here's your challenge. Is there a hole, an asymptote, or both for the function k of x equals x minus 5 times x plus 4 over x minus 5 times x minus 1? Think it through. what factors can cancel, what makes the denominator 0, what's left after cancellation. Work through the problem step by step and share your solution in the comments below. Now you'll never confuse wholes and asymptotes again. Remember, cancellation means whole, denominator 0 without cancellation means asymptote. Thanks for watching. Like, subscribe, and don't forget, math success starts when you stay on the fast track.